Of where we started last time. We graphed the parent function of the quadratic, okay? And it looks like what we called a parabola. Its vertex was at 0, 0. If you didn't mark on your paper that number 1 was the parent function. Okay? So then when we looked at number 2 and number 3, what value was being changed from the parent function? The a, the h, or the k of the vertex form? The a value. So we were concentrating on what is changing this due to the graph. Okay? So what did it do to the graph? Eric? Okay, so stretches and compresses it vertically or horizontally? Vertically, because the 3 and the negative 1/2 are not part of what is being squared. That's how I know they're a vertical stretch or a vertical compression. So glance back at your organizer on the back. Look at vertical stretches and compressions. And remember that for vertical stretches and compressions, we made notation like this, where the a was the number multiplying outside of the function. The 3 is not part of what is being squared, and neither is the negative 1/2, which is how I know that those are vertical interpretations of what's happening in the graph. All right, so 3 being greater than 1 as a vertical change, it's going to stretch it, where 1/2 being less than 1 is going to compress the graph. Okay? What do we call this negative part? Eric was right. It flips it upside down. Well, what was our transformation label for that? Good. It's a vertical reflection, so from up to down, or a reflection over the x-axis. Does that make sense to everybody? Okay. So we're trying to use more of this language. So stuff you should have written over here, okay, that this was a vertical stretch. This was a vertical compression with the 1/2. And also it was a vertical reflection. Okay. So those are some things that should stand out. So again, taking that A, H, K stuff like we did with absolute value, but taking it one step further to understand it in that transformation language instead of just, oh, it makes it narrower, wider, okay? We want to use the correct math vocab. So 4 and 5, what value is being adjusted? Helen? Is this so the H value is when it's shifting inside, so the K value. So in these cases, we were adjusting the K value. The A and the H would be the same as the parent function. What did adjusting the K value do to your graph of your parabola? Raven? Good. It moved it up or down. And it was kind of how you saw it, right? Like if it was positive 1, it moved it up 1. And if it was negative 4, it moved it down 4. Okay? So if you look back at the back of your organizer about what transformation that is, what is the transformation that causes shifting on the graph? Alex? Okay, this is horizontal. Oh, no, this one's not horizontal, actually. It's translations. Okay, so these are translations. So both of these graphs were translated because they were shifted. Were they translated vertically or horizontally? Vertically. So like, remember on your organizer, at first the notation seemed weird, but hopefully we're getting a little bit used to it. It was the function, and then after the function was done, it said plus or minus k, right? Like a number came added or subtracted afterwards. That's what's happening right here. Our squaring was all done, and then we added something, and then we subtracted something. That's what's making it a vertical translation. Okay, so this graph was specifically translated up 1 unit, and this graph was specifically translated down 4 units. Okay? All right, so in 6 and 7, there was still stuff being added and subtracted, but what kind of changes did you see in the graph here? Okay, good. So these were translations happening horizontally, and if you look back at your organizer, our notation looks like this, and notice it's still adding and subtracting a value, but this value happens now inside the parentheses. That notation is saying it's happening inside the function. So see here when you were adding and subtracting stuff, how it was inside what was being squared? That's why it's a horizontal change instead of a vertical change. Okay? So she's right, they're translated horizontally. What is the H value for number 6? Helen? And for number 7? 2. Are you guys okay with the negativity and positivity of those values? So in this case, in number 6, it was translated horizontally. Specifically, it was translated 3 units to the left. And then in number 7, it was translated 2 units to the right. Yes? Mm-hmm. Uh-huh. Well, it's not, no. So it's, no. So in the formula, I get what you're saying, but it just needs to be tightened up a little bit. They put a minus in the formula, which kind of makes you pick out the opposite value than what you see. Like here I see a plus, that really means the H value is negative 3. Why they did that in the formula is that you do see H as negative 3, so it is shifted to the left 3. Okay? So the H value is telling you what is happening, exactly what is happening. Minus 3 is left 3 and positive 2 is right 2. But it doesn't look like a minus 3 when you just glance at the equation because you have to understand how they built it. And they didn't build it that way to be confusing. They built it that way so that when you pick out the number, it is telling you the correct translation. Okay? Any other questions about that? So the horizontal stuff is tricky, right? Look again at the back of your transformations. Okay? When you add or subtract k at the very end, the vertical transformations, it's exactly what you see. Plus 5 is up 5, minus 1 is down 1. But when we do it with the horizontal ones, we have to be really careful about picking out the right h value so we see whether it's going left or right, right? And then the same thing with vertical stretches and compressions. Back here, it was exactly what we thought it would be. Okay? 3, a factor of 3, something bigger than 1 is a vertical stretch, and a factor of 1/2 is a vertical compression. But if you look at what we did on the horizontal stretches and compressions with the radical function there, they're kind of the opposite of what you think. So it's a little harder to look at the equation and understand thoroughly the horizontal stuff that's going on. The vertical stuff is a little bit easier, right? And the horizontal stuff is all happening inside the function, and the vertical stuff, all those transformations are happening after the function is done. Okay? So does this help connect a little bit those things that you were seeing in the graph and kind of like what you were seeing and understood to this math vocabulary that we're using on the back of your organizer? All right, so now that we know what everything does, at the bottom it says, think about these transformations. Can you name all of the transformations that would take place from the parent function, which would just be f of x equals x squared, to obtain the graph of g of x equals that big equation up there? So what are all the things you would have to do to this poor little x squared parabola sitting on the graph to get it to become that other function? Sean, give me one of the transformations. Okay, good. What was the second part? Okay, so it's translated up 3 and left 5. Are you guys fine with how he picked out those values? So he's looking at the h and k values. The 3, a plus 3 really is a plus 3. When I see plus 5, I have to think about the fact that that's really minus a negative, so the h is negative 5, and that's why it's a shift left 5. Jenny? Okay, good. So there's a reflection. You would either say it's a vertical reflection, or you would say reflection over the x-axis. That is because of what part of the equation? Cody? You were going to give me another one? All right. What part of the equation is telling me there's a reflection going on? Matt? The negative part of it. Good. And the negative's not happening within the squaring part. It's happening outside of it, which is telling me it's a vertical change that's happening. All right, another change that we see. Cody?
Vertical stretch by 4.
Okay, good. So we see a vertical stretch by a factor of 4. And that means all those vertical heights we would see in the parent graph, those are going 4 times as high as they would have normally gone. Like we're grabbing the paper and stretching it 4 times as big. Matt?
So, if it was like negative, or if it was 4 times like negative x minus 5, then that would be a reflection across the y-axis.
Yeah, so let's say we had another function like this. 4 right? So he wants to say, let's say we were looking at this equation and there was more stuff happening inside of the squaring part of it. And each function, the horizontal stuff gets a little tricky because in some of the functions you can factor that part out and view it a different way. So sometimes you can see something and some person might say, well, that is a horizontal stretch or compression. And someone else might interpret it as a different vertical stretch or compression if they rewrote the equation. Okay? But looking at the equation as it is, the only thing you would have to do is you would have to factor out the negative to see clearly what's happening. Otherwise, you're not seeing your real shift. You're seeing the shift that has had this negative affect it. So we want to look at the negative on its own, and then we can see the shifting. So we want each part of it to kind of be on its own. So if we looked at this, we would still have that we would be shifted or translated 3 units up and 5 units to the left. We would still have a vertical stretch by a factor of 4, but because this negative is inside the radical, it would represent a reflection over the y-axis or a horizontal reflection from left to right. Julia?
If you had a negative like that in the equation, but then you also had one that was 4, would that cancel each other out?
Not always. It's going to depend on how the function looks. So some functions are more symmetrical than others, right? Like absolute value and quadratics have like that line of symmetry where they're the same on both sides. So sometimes certain reflections, you wouldn't even notice there was a reflection because it might look the same way flipped over that it looked before. Okay? But in some functions, those negatives would be very different. Like in the greatest integer function, for example, that stair step one that we did. So one of these is a vertical reflection. So here was originally our stair steps, right? And they were open on this side and closed on this side. So a reflection that flips it from left to right is going to flip it over here so that the endpoints would appear in different orders and it would go in a different direction. But the one that flips it just up and down, the endpoints would still go in the same order, but it would just go a different direction. So it depends on the function and how the function works, whether these end up like changing each other so that it's the same or not. So it's different for each type of function. Okay. Does that help clarify some of that stuff for you guys, that there could be these different situations? But if you can look at each part separately, you can identify what type of change it is on the graph. Okay, so again, we're working on that throughout our whole course. Every type of function we learn to graph, we want to see these transformations. And those notes on the back of there, those are going to be the same for every function. Okay, we're going to refer to the same types of things. We're not going to change it up. All right? Okay, so some more concrete examples to help you get through tonight's homework a little bit. I'm sad that it doesn't fit. Okay, so if we wanted to graph this function, so now you should look at it. When you see the little squared, what should immediately pop into your head? What should you be thinking? Yeah, parabola, immediately. So you see absolute value bars, you're thinking V. You see something squared, okay, a quadratic, you're thinking parabola. Then you should think what you know about that parabola. So it's been written in kind of the most convenient way to use transformations because it's written in that vertex form where we can look for all those different shifts, okay, translations, reflections, and then also stretches and compressions. Okay? So something that we can pick out from this graph if we want to get it right away. Notice the first question I asked you, what is the vertex? Okay, good. So the vertex is going to be 3, -5. I'm going to write the equation over here because my screen is going to get in the way when I do this. Is everybody okay with how Eric picked out the vertex as 3, -5? So we're looking for that h and k value. So we're getting 3, -5 as my vertex. Now, do you guys expect this parabola to go upward or downward? Upward. Do you expect it to be kind of the same rates of change on the edges as the parent function, or do you expect it to be stretched or compressed? Compressed vertically or horizontally? Vertically. Good. Okay, so we have a picture in our head. We have this upward U, a little more kind of short and squatty than the other one. So see how those transformations help you like immediately relate equation to graph. They're no longer separate. They are now like this interconnected world where we see them together. Okay. So 3, -5 is actually something I can put onto the graph. So 3, -5. Yes. we'll go through it in a minute. Yeah, we'll get there. All right, what's the axis of symmetry? Cody?
X equals 3.
Good, x equals 3. We know our parabola in this case is up or down. We're going to see some later on in our course that can face left or right. But right now we're kind of in this situation, so our symmetrical axis is always going to be some sort of vertical line on our graph. Okay, what is the minimum? So this is kind of a weird question. I want you to understand the language thoroughly. So what is the minimum of our graph? I see Eric and I see Helen, and I want you to the vertex. Okay, so the vertex can be either the minimum or it could be the maximum of any given parabola. Do you guys understand that? Because it's either going to be the place that it bottoms out or the place that it reaches the very top of the graph. Nothing can go past it with this shape, right? Unless we curve around again, that's not a parabola anymore. So our minimum is the point 3, -5. It is our vertex point. But then sometimes when people ask for the minimum, you have to be really careful what they're asking about. I just asked you for the minimum. So that's kind of like a broad statement. You're identifying graphically where the minimum point is. But they could ask you for the minimum value or where the minimum occurs. Okay? Now, those are different questions. If your minimum is the point 3, -5, what do you believe is the minimum value? Helen? No. No? David? Well, if you plug the point into the equation, all that's going to happen is you're going to verify that it's actually in the equation, so you would just get two numbers equal to each other. Okay? What is the minimum value you reach on the graph? -5. Good. So minimum value is saying there is a function. You plug some stuff in, and then it reaches these different values. So value is kind of a term referring to the y-coordinate, like the outcome of the equation. So in this case, the minimum value is -5. Why I'm pointing this out is because this is a different question than this. What is the minimum versus what is the minimum value? Very different. It's like your profit models that you guys were analyzing, right? There's like places where the minimum occurs, but then there's a whole different equation you plug that into to tell me what the minimum profit actually is, right? So this is that same idea. This is the minimum point, and that means this is the smallest value that our function reaches, -5. Now, where does that value occur at on the graph? 3, okay? So where this could come important, think about the little horse jumping over the gate that you guys did in your math moment, right? That silly little problem. Where it could come important is if you need to know like how high to make the gates for the competition of the jumps or something like that, you would just want to know the maximum value, right? You don't need a coordinate pair. You need to know what is the actual maximum height that I can reach. Okay? Whereas if you were the person jumping the horse, you'd really want to know, okay, where does that happen at? Because you have to gauge when you're actually going to press that jump button or whatever the case may be. Okay? So these get interpreted different ways in real life situations, so it's important that we understand that language. All right, domain and range. So there was a question in homework number 1 about domain and range, so I apologize because we hadn't really talked about it yet. So domain of the graph is normally what? You guys have some previous knowledge of what you think that this is. Jordan? X. So we think domain, X. So that's really easy when someone gives you a list of points, right? You guys just pick out all the X values and you're like, yay, domain, right? Done. And then all the Y values give you your range. It gets a little more complicated than that because this is a whole entire equation, right? So what is the domain of this equation? All real numbers. Do you guys know why he's saying that? So basically, when you're trying to look for the domain, like what am I allowed to use for X, the easiest way to look for what you're allowed to use for X is to look and see if there's anything you are not allowed to use for X. Okay? And what I mean you're allowed to use for X is when we finish graphing this, we're going to look at this x-axis and see, is there any point that if I tried to plug in that x value, it does not correspond to a point on my graph? Then that is something I better not include in my domain. And I'll figure out if there's certain areas on the graph that I have to exclude or something like that. So let's finish graphing it first because it'll give you guys a good picture of what's going on. And then we'll answer the domain and the range question. So when I'm graphing one of these functions, there's two ways to do it. So we're going to answer Eric's question about, like, I know how the parent function works. So how does this whole vertical compression and stretch thing work? Or we can just basically plug in points. Okay? So one way is, once you have your vertex and your axis of symmetry, you could just go and plug in a point on one side of your axis of symmetry. to get something. So my axis of symmetry is at 3. I don't want to go too far away or my graph's going to like shoot way off where I can't reach it anymore. So maybe I'd plug in like 2 as an x value, right? So one way that I could get another point on my graph is I could just take my equation. I could plug in 2 as an x value. I chose that. I chose it based on where my axis of symmetry was.
Sorry,
Uh-huh.
going back to the minimum, will it always be the vertex?
The vertex will always be the minimum or the maximum, but it depends on which way the parabola faces. Okay? All right, so here's my equation. I'm just going to figure out what the y value is that goes with this x value. So 2 minus 3 is negative 1. Negative 1 squared is just 1, so that's not going to change the 1/2 when it multiplies it. And 1/2 minus 5 is negative 4 and 1/2. So I plugged in 2. I got negative 4 and 1/2, which is like here. I could put that on the other side. I could plug in another point if I want, okay? And then I could get my curve. Yes?
I was just curious, like the 1/2,
Mm-hmm.
use that as almost like a slope and do that on both sides?
Yeah, so let's talk about, that addresses your question as well as Eric's question about how to kind of transform it from the parent without having to plug in points. So you learned all these transformations, right? It'd be useful if you could actually take the transformation and just figure out the graph without having to plug in a point. And an absolute value was really easy because that a value just became the slopes of the sides because they were perfectly straight lines, right? In this case, it's not as simple because you can't just keep going up some amount and over the same amount. You're going to get linear sides instead of these curved sides. But what you can think about is what happens in the parent function. So in the parent function of x squared, from the vertex, when you go over 1 unit, how much higher than the vertex do you end up? So like when you plug in 1, what do you get as the y value? 1, when you're just doing x squared, right? So 1 unit away from the vertex horizontally, those points are 1 unit above it. Okay? Whereas when you're 2 units away from the vertex horizontally, how far above it are you? 4. So 1, 2, 3, 4. Now remember, all we're doing here is vertically stretching or compressing our graph. So we're not changing any of these horizontal distances. We're only changing the vertical distance by our stretch or compression. And this time our factor is 1/2, so it's compressing it. So basically, this used to be 1 unit above the vertex when you were 1 unit away. If I've taken that and compressed it so that it's 1/2 times as big as it used to be, how far vertically did that distance just move? So normally it was 1, and I just compressed it so it's half as big. So instead of being a distance of 1, it's now going to be a distance of 1/2. So you could go over 1, up 1/2. Notice that's where my point ended up, right? If you plotted the point 2 units away from the vertex, normally that meant that the vertical distance from where the vertex had been and where it ended up was now 4 units away from each other, like this distance right here. Okay, it was normally 4. But now I've taken it and I've compressed it by a factor of 1/2. So it went from 4 down to half of 4, which is what? 2. So if I wanted to, then 2 units away, I would expect to be 2 units above. Helen? Okay. So you can either plot a point to get those side points, or you can use the transformation, but notice it's a little bit different than just using a consistent slope, so we don't really refer to it as slope. You have to think about how does the parent function behave vertically. Now I'm going to change those numbers by this factor. Okay? All right, so back to domain and range idea. So domain is the x values that you're allowed to plug in. So did I tell you guys that my friend has like a Jay-Z finger puppet? She's a teacher friend, and she has this Jay-Z finger puppet. She's like a teaching apron, okay? She's very prepared, all right? So she has a Jay-Z finger puppet to describe domain, because she says, oh, think about Jay-Z walking across the stage, right? Is there a part where the stage would just like fall off the edge of the earth? Is there a hole in the stage that he's going to fall through? And that's what you want to think about when you're thinking about domain. As you move across the x-axis and you pick x values, would you for sure end up somewhere on your graph, or are you going to hit a hole or a place where the graph has end and you're going to fall off the stage? Okay? So pick any x value. Let's say I pick this x value right here. Okay? Is there a corresponding point on my graph? Sure. Right? Let's say I pick an x value out here. Is there going to be a corresponding point on the graph? It's going to be really high up there, but there will be one. Right? can you guys determine any x value that if you tried to use it, you would not be able to see a point on that graph? No. If you pick one out here, there's going to be a point. It's going to be way, 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 way up there, right? Because of the way the parabola grows. That means any x value you pick works in the equation, so to speak. You'll be able to finish the calculation. It might not be pretty. It might be the ugliest number you've ever seen. But if you plug that x value in, you will get some calculation out. You will get some point on your graph. Okay? So if there's no holes and there's no places where like the graph just ends, then every x value can be plugged into this equation and obtain a y value, which means you can use any x value for the domain, and any x value in this case is going to be described as all real numbers. So the range, you guys said, is y values. So in our case, we have to just shift our perspective to a vertical perspective for our graph. So instead of JZ, she tells her class to think about Spider-Man because he like climbs up and down buildings. Like, what if there's an open window? There goes Spider-Man, right? This kind of idea. So, or the building ends, he can't go any higher, right? This kind of idea. So she thinks about Spider-Man. Apparently, I need finger puppets, and I'll do really good with this, right? So think about Spider-Man moving up and down your graph. Can he move forever upward on this graph? Could he grab onto the graph and climb it and just keep climbing up? Yeah, no limit, right? Okay. What about going down the graph? No. He eventually hits, our graph ends right here. So if he's connected to our graph, he cannot go below this point, right? So that means that our range is limited in this case. It's not everything, okay? It's this point right here and everything above it, right? So how do we describe that? Good. And we use y as the variable in the range because the range is describing the y values, like you guys talked about, just kind of in a broader sense maybe than you're used to. So the y value is greater than or equal to -5. Is that okay for some conceptual ideas of domain and range? You're just going to be thinking about Jay-Z and Spider-Man now all the time? Yeah. Okay. If you wrote it with bracket notations, the way that you have to write it is this. So this is like not really a notation. This is just describing it. We'll get into notation later. But there is set notation and there is bracket notation. In set notation, this would say y is what I'm using, and you would write y is greater than or equal to -5. Okay. In bracket notation, you want to write the minimum, comma, the maximum, and use a different bracket depending on if it's included or not. So -5 is our minimum. And we would include a bracket because it is included. That's not greatest integer function. That's just a bracket. Okay. And then, yes, it doesn't end, so it would go to infinity. You can't ever actually reach infinity, right, because it's this idea, not this specific number. So it has a parenthesis there saying you don't actually reach that value. Sean?
The parabola reflected downward. Would y be less than or equal to -5?
Yes. Make sense? Okay. All right, so that brings us to the last part is we want to name all the transformations that occurred on this graph. So we talked about them while we were graphing them. Tell them to me. What were the transformations that happened to get the parent function to turn into this graph? Helen, give me one. Good. We did a vertical compression. Okay. Yes.
Vertical translation down 5.
Okay, good. We did a vertical translation down 5. Raven? Good. And we horizontally translated it to the right 3. So do you see how knowing those transformations really helps you kind of understand where the picture of your graph should be? So if you know shapes and you know transformations, you can graph stuff a lot faster than you might have been able to in the past. Okay? And it will become more natural. And the cool thing, again, is this carries throughout every function. It's not like you have to learn all these transformations for quadratics, and then they're going to be different for something else. They're going to be the same. Okay? All right. So, your turn. Okay. Eyes back up here. We're going to check what you guys did. So first of all, everybody okay with the vertex at -5, 2? Okay. Which means our axis of symmetry is the vertical line x equals -5. And that our maximum, okay, is -5, 2. To translate that, that means the maximum value, the highest point your graph reaches, is 2, and that is happening at or occurs at -5. Okay? The domain, again, is all real numbers. Is that going to change for any of our quadratics, our parabolas? No, we don't have any limitations on what we plug in xy's, but the range is going to keep changing depending upon our vertex and whether or not our parabola was reflected, right? So can somebody give me the range for this parabola? Bailey? Good. Y is less than or equal to 2, okay? Because 2 is our maximum value. All right, give me the transformations. Let's hear them. Let's see, who hasn't talked to me yet today? How about new people? Okay, Monet, give us a transformation. Good. So one transformation is it translated up 2 units. Okay, another one. Claire. Good. It translated to the left 5 units because their h is equal to -5. All right, what else? Dana. Good. It's stretched vertically by a factor of 3. And our final transformation. Yes, Julia. Good. A reflection over the x-axis. And you might think, like, that didn't reflect over the x-axis. But it did, because what would have happened is it would have been, like, down here and then flipped over. Okay? So reflection over the x-axis from up to down. Or you could have said vertical reflection. I'm okay with that. Good. Feeling a little more comfortable with the language? Yes. Yes, or vertical reflection. Then there isn't any reflection to talk about. Okay? Yes, Sean. Uh-huh. Okay, so negative just tells me downward instead of upward. And what the stretch of 3 tells me, again, is normally in my most basic parent function from the vertex, if I go over 1 unit, I go up 1 unit. Okay? If I'm vertically stretching this by a factor of 3, instead of going up 1, I'm going up 1 times 3, which means it's going to be 3 units away vertically instead of 1. Okay? Claire?
I'm confused because on this it says that it's negative, then it's over the y-axis, so why is
Does it say, because, last example. Okay, so the arch of the Sydney Harbour Bridge is approximately 500 meters long and 85 meters high. Write the quadratic function. Oh, what quadratic function models the curve of the arch? So you have this arch. I'm sorry, I have to draw. I don't draw well. I just need to draw to figure out what's happening. Okay. They tell me it's about 500 meters long and 85 meters high. Okay. And I'm supposed to figure out, okay, what's happening here, or how to write an equation that represents. And they say I can assume that this is like a 0, 0. All right, so if we want to write an equation, first of all. Eric, I know you're eager. I just got to make sure everyone's with us on the same page. All right, so we want to set it up so we can fill this in, which means we want to know the h, the k, and the a value. So let's focus first on the h and the k value. Can somebody give me some idea of what the vertex is? Eric, go ahead. So the vertex is the maximum or minimum point. Okay. We know it reaches a maximum height at 85, so that's that value, that y coordinate. And in this case, we know it's at 250 because of the 500 being the entire span, right? Okay. So we basically have our h value and our k value. So you're going to come across a couple of problems like this in the homework. James can tell you that it's true, right? Okay, so the question is, how do you find an a value of an equation if you've come up so far with like the h and the k values of the equation? So what kind of information? So independent of this problem for a minute. If you were just looking at this and you really needed to find the a value, what do you think would be a useful piece of information about the parabola that you could use to find the a value? Matt.
So you could use like the 2 solutions, which are 0, 0, and 500, 0.
Okay, so one thing he's identifying is there are some points here that are solutions, as well as, which means they're x-intercepts. They're also points on the parabola. Eric, another idea? Between these two locations? Okay. What else? Other ideas? All right, let me refer to something you guys know from the past. You don't have to write this down, but a little review. Let's say that I told you guys there was a slope of a line, and its slope was 2, and I wanted you to write the equation of the line. You could immediately write this, right? But in order for your equation to be complete, you would have to find this b value. What other piece of information do you usually use to find that b value or any other missing part of your equation to finish the equation of your line? Okay? Good. Any point on that line, right? So this is the key. If I know any point on that line, I get to plug these numbers in temporarily for x and y. And once these things are numbers, what's the only variable left? B. Can I figure out B then? Yeah, and then I go back up here and just fill in that B value. So anytime you have an equation and you're just missing one part of that equation that you need to find, search and see if they give you any other points on your parabola, whether it's graphically and you can see the point and you can pick out the coordinates, okay? Or whether it's they say your quadratic passes through this other point. Okay, then they're just giving the information to you. But the idea is if we know some other point, right, we can plug in that other point. And it doesn't have to be a special point like this one is. It doesn't have to be the solution. And we can finish solving this problem now to find the a value. Okay? So I don't know. What's 250 squared?
62,500.
Oh, I should have known that, actually. No, that's not too bad. It's 25 times 25 is 625. So, okay. Okay, so our a value is negative 85 divided by 62,500. Negative 0.00136. Yeah? Yeah. If you use the 0, point, you didn't get that answer. Now, when you write your final answer needs to be this with that a value right there. So make sure you go back and you write your final equation